Welcome everyone to this channel, and thank you for sharing content like this with your friends. I want to encourage you to continue to do so. In this particular video, we are going to be answering the Cambridge IGCSE Chemistry Paper 6, which is an alternative to practical. And you can see that it's a very recent paper, October-November 2023. So it's a paper that is timely as well. So I want you to follow through and learn as much as possible, and always drop some comments at the end of the video. Okay, so we go straight to the questions. All right, so the first one says a student uses chromatography to analyze samples of 3 different dyes. And then this is the setup for as shown in the figure. So what the question wants us to do first is to draw 3 spots to show where the 3 dyes are placed on the paper at the start of the experiment, and also a line to show the level of ethanol in the beaker at the start of the experiment. So we go straight to doing that. Now, the 3 spots should be on the baseline, so we can just, put the 3 spots right here. So this is the first spot, the second spot, that has to be properly spaced, and this is the 3rd spot. So that is for the first question there that has been answered. So you could make the 3 dots and make sure they are on the baseline. Now the next one says a line to show the level of ethanol in the beaker at the start of the experiment. Now you need to be careful here. The level of the level of ethanol should be below the baseline, so somewhere around here, so that there is a point at which the ethanol rises all the way to where the spots are. Okay, so it has to be, okay, you could just use a line there to demonstrate, to show the level of ethanol. It doesn't have to be too close to the baseline. Okay, you have to give some distance so that the solvent can travel to where the spots are. Okay, and that should get you the 2 marks for this particular question. So move forward to the next one. It says during the experiment, ethanol moves up the paper. Okay, so states when the student should remove the chromatography paper from the ethanol in the beaker. So the students can remove the chromatography paper from the ethanol in the beaker when the ethanol has gotten to almost the top of the paper. Okay, so when the ethanol is almost at the top of the paper. So when the ethanol is almost at the top of the paper. When the ethanol is almost at the top of the paper. And why should we allow this to happen? So that you can have a proper separation. Okay, so you have to allow the ethanol properly dissolve the spots, okay, and get to almost the top of the paper where all the components have separated before you remove the chromatography paper. So that's the principle behind it. Now figure 1.2 shows the results of the chromatography experiment. So state what conclusions can be made from this result. So there are 3 dyes here, dye 1, dye 2, dye 3. Now what first conclusion we can simply make from this result is that the dyes are soluble in the solvent. Okay, so the dyes are soluble in the solvent. So that's one conclusion. And how are we able to know, how are we able to make such conclusions? Because each dye separates into various components. That means the dyes are soluble in the solvent. Another conclusion we can make is to compare dye 1 and dye 3, just having a single component. So that tells us that dye 1 and dye 3 are pure substances. Dye 1 and 3 are pure substances, and that is why they contain just a single component. So that's an information you can extract from this diagram. There's a 3rd extraction that could also be gotten. Okay, you could look at dye 2, okay, dye 1 and dye 2, and also compare dye 2 and dye 3. So you could also conclude that dye 2 contains dye 1 and dye 3. Okay, so dye 2 has some components of dye 1 because it has a similar components in terms of the distance traveled by this particular one, and also in this case, it has the same distance. So we can say that die 2, okay, contains die 1 and die 3. That would be a third conclusion as far as that figure is concerned. But we are looking at 2 marks for 2 points that have been made. So for that, I think we are done with question 1. So we'll go straight to question 2 just to save time. Now, I would not read all the whole information here. I will just try and summarize it. Now, in this experiment, we're trying to use copper 2 carbonate, reacting with the dilute acid, and the dilute acid in this case is diluted with ethanoic acid. And then the powdered copper 2 carbonate, which is also known as the powdered malachite, is observed at different temperatures. So at these different temperatures, the student does it in 6 separate experiments. All right, and this is the setup for the whole experiment and each detail of what happens in each of the experiments. All right, so because of our time, we'll just go straight to answering the questions involved in this particular question number. So what the first question wants us to do is to simply pick out the temperature readings on the thermometer and on the stop clock. So that's what we'll do as fast as possible. So if you look at the thermometer reading, look at the calibration, you see that each small line represents 1 unit. So this is simply 21, 22, 23, 24, 25. And if you look at the reading up here, this is 25, so this is 26. But the reading is in between 26 and 27. So that's simply 26.5, okay, because the reading stays in between. So that is how to read the thermometer, okay, for the alternative to practical. So look at the second one, it has to be 31. So don't just write 31, it has to be 31.0 because you have to maintain the same decimal place for all of the readings. As far as the temperature is concerned, that could also earn you the right mark. So always learn to maintain the same decimal places or the same significant figure as the case may apply. So the next one is, from our reading here, is 36.0, not just 36. The next one is 42.0 from the reading there. And we also have the next one to be 53.0. All right. And the last one there, if you look at it carefully, it lies in between 60 and 59. And for that, it has to be 59.5. Right? You can see all our results are in 1 decimal place. Now we go straight to the time taking. Looking at the time taking, we see that the outer circle here represents the seconds, the inner circle represents minutes. So if you look at it, each small line, each tiny line here represents 1 unit as well. So if you count these lines and add it up to 30, we are looking at around 42 seconds. All right, we're looking at about 42 seconds. So that is for that. 42 seconds for the outer circle. Now, if you look at the inner one, you see that 1, 2, 3, 4 is about 4 minutes. All right. So 42 seconds, 4 minutes for the first experiment. And from the table of values, our data or the value should be uniform in seconds. So what we need to do is to make all of these uniform to seconds. And that's simply done by converting the 4 minutes to seconds. So the conversion is simply, remember that 60 seconds is equivalent to 1 minute. So if 60 seconds is equivalent to 1 minute, 4 minutes will simply give 60 times 4, and that is 240 seconds. So 4 minutes is equivalent to 240 seconds. So 240 seconds plus 42 seconds gives you 282 seconds for the first reading. So that is how you would solve for other values there. So because of time, I'll just be setting the reading based on what I have done already. So to save time, this is 195 seconds. And I think I'll explain the last experiment 6, just to be sure that we understand how it is gotten. So this is 10 seconds. All right, we move all the way to the next one. This is 65 seconds. And for this one, if you look at it, it's close to 45. So that's 44. So we have 44 seconds here. Then if you look at the reading for the minute, it's 0 minutes. So 44 seconds, 0 minutes, which is equivalent to 44. So what do you notice about these readings? The temperature is everything is uniform in terms of how the values are represented, just one decimal place. And then for the time taken to collect the gases is also uniform, and that is what earns you the mark. To ensure that your decimal places are uniform and your significant figures are equally uniform to get the full marks allocated for that particular question. And that's all for that. So the next thing is to put all this information into plots. Now, if you look at the graph here, we see that the x-axis is the temperature of ethanoic acid. The scale has been given already, but the question here says complete a suitable scale on the y-axis and plot the results from experiment 1 to 6 on figure 2.2, and then you draw a line of best fit through your points. So we're going to do that quickly. Now, if you look at the time taken to collect 100 centimeter cube of the gas per second, we see that the highest value is about 282. So what the scale I will adopt is this. Okay, so for every 10 boxes, I'll just allocate 50 units there. So for every 10 boxes, 50 units. So this is 100. For another 10 boxes, 150. For another 10, 200. Right? For another 10, 250. And then for another 10, this up here is about 300. Let's do this well so that it's clear enough. So right up here, I'm going to label it 300. All right, so we've gotten the scale for the y-axis. That's the first step. The second step is to plot now, following the data that we've obtained. So let's start from the first data there. 26.5 on the x-axis, 282 on the y-axis. So we're looking at 26.5. Each of the units here represents 1 unit. So this is 21, 22, 23, 24, 25, 26.5 is somewhere at the middle. Okay, at the middle here. And then 282 is way above here. So if we look at this scale for the y-axis, so if 10 boxes are 50 units, that means each box is 5 units. So if each box is 5 units, that means this is 255, 260, 265, 270, 275, 280. So 282 is just around this 280 spots, okay? So if we trace that, let's see, if we trace that, so we trace this line all the way up here, we see that we have okay, so we have it somewhere around there, all right? So let's go straight to the next one so we don't spend too much time. 3195, 3195. So 31 is somewhere around here. So 195. This is 155. Okay, if this is 200, so 195 should be, I think, somewhere around there, right? If we are dealing with 195, okay, and each line is 5 units. So 195 should be around there. So we trace it again, and we'd have something like this. Please bear with me with the way I'm plotting this. Okay, so 195 is somewhere around there because this is 200. Let's write this well so that it's not confusing. This is 200. So 195 is somewhere around there. So we'll move again to the next reading. 36,148. So 36, 148. This is 31, 32, 33, 34, 35, 36. 36 is somewhere around here. So we have to look for 148. So this is 105, 110, 115, 120, 125, 130, 145, 105, 110, 115, 120, 125, 130, 135, 140, 145. Okay, since this is 148, we are looking at very close to 150. So let's just save time, please. So we get, let's just keep it, let's just put it here. Okay, kind of somewhere around there. Right, I think we got that right. All right, so that's for that. Now we go to the next one, 42,110. So 42,110. 42 is somewhere around, if this is 45, so 42 should be around the middle where we have 40 kind of. And then, sorry, 42, let's look at the values again. 42 on the x-axis, sorry, 110 on the right, on the y-axis rather. So 42 is somewhere here, and 110 is 15110. So this is 110. So we trace that, it's on the second line. So we have something around, trying to see this clearly so that at least you can have something close to what we are supposed to have. Okay, so the next one is 5365. So 53 on the x-axis, this is 53, and then 65. So this is like 55, 60, 65. So 53 here, so we trace it, and it's like 55, 65, so somewhere around here, right? Right, so I think that's that for that. And then the last one, 59.5, is about 60, 44. So it's about 60 and then 44. 44 should be, let's see, so this is, okay, I think we did 40. So this is 5, 10, 15, 20, 25, 30, 35, 40. So 44 should be somewhere around here. So 44 should be around there. And then we're looking at about 60. So you can just, you know, keep it somewhere here, okay, just to, you know, get it. So we have 6 plots there, 1, 2, 3, 4, 5, 6. Now the next thing is to draw the line of best fit. Now you have to manage this line because it's not really easy drawing on the screen. Just bear with me. Let's try to draw. Okay. So we may not really have a perfect curve, right? But ensure that the curve touches all the lines, right? So that is how it's going to look like, kind of, okay? Because it's on the screen, you might not really get a perfect plot, but when you're doing it on paper, of course, you should have something perfect and better than this, all right? So, but the idea is understood, okay, to ensure that most of the points get into the curve, okay, and I believe that will have been possible. That should be possible here. Let me clean this. Let's try once again to ensure that we capture most of sorry. Right, so let's see if we're not going to spend too much time here. See if we can capture something. Okay, I think it's capture that line. Okay, I think I've captured most of the lines, so just bear with the curve, like I said. So that should earn us the mark for that question, all right? So that's just what the question wants you to do. So the context is clear. So move to C now. It says average rate of reaction is the volume of gas collected divided by the time taken to collect the gas. So we have to use this equation to calculate the rate of reaction in experiment 6. All right, so if we have to calculate the rate of reaction in experiment 6, we use the volume of the gas collected and then we divide it by the time taken to collect the gas. So if you look at the whole experiment entirely, you see that the volume of gas collected is simply 100 centimeter cube. And then the time taken to collect the gas for experiment 6, we go all the way to where we have experiment 6. What was the time taken? This was the time taken to collect that volume. So 100 divided by 44, we get us our answer. So we could use the calculator now to see. So we do that, you have 2.27. So 2.27 is what we have when you perform that. And then you, of course, you have to include the unit, centimeter cube per second. And that should earn you the 2 marks there. If that's clear enough. So deduce in which experiment the rate of reaction is greatest. So for us to know where the rate of reaction is greatest, we have to simply divide the volume by the time taken for each of the experiments. All right. So we're going to do volume divided by time taken for each of the experiments to know how the rate of reaction varies in all of them. So let's just do a couple of them and see what we obtain. So the first one will be 100 divided by 282. And if you do 100 divided by 282, the rate here is 0.35. So we do the same thing there, 100 divided by 195 for the second experiment. And we're having 0.51. So we do the same thing for the third one, 100 divided by 148. We have 0.67 here. So we scroll again, we do it here, 100 divided by 110. And we have 0.91 in this case, and then 100 divided by 65, we have 1.53, and then 100 divided by 44, what we had was 2. I think what we had here was 2.27. So if you look at all these values from the first experiment to the second experiment, you observe that experiment 6 has the largest rate of 2.27, greater than every other one. So we go back to our answer here. So deducing which experiment, so all we just need to do is to say that the include, just write 6 since you are asked just to indicate which experiment. So experiment 6 is the greatest because it has the greatest average rate of reaction. I believe that is clear enough. All right, so the next question says extend the line on your graph in figure 2.2. Deduce the time taken to collect 100 centimeter cube of gas when the temperature of the ethanoic acid is 65 degrees. So we go to the graph. Remember that the temperature is on the x-axis. So we extend this graph to 65. So this is 61, 62, 63, 64, 64, 65. So this is 65, right? So we can just manage and extend it to this point. All right. So if you extend to that point, we now pick your ruler, wherever the extended line touches 65, trace it all the way to the y-axis. So I'm going to do that here, but it's going to be, so we just trace it gradually because that is where it touches the y-axis. So you trace it, trace it, trace it, trace it. Not having a perfect straight line here, but the concept is understood. So when you trace it that way, we now 5, 10, 15, 20, 25, 30, 35. So you can see that it is 35 seconds from my own graph. Okay, so 35 seconds from my graph. Let's confirm again. This is 5, 10, 15, 20, 25, 30, 35. Yeah, 40, 45, 50. So it's 35 seconds. So that is how you do such, just trace it. Make sure that you have a good curve so that you can look at where it touches 65 degrees Celsius and you extrapolate it to where we have the y-axis and you get the value of what you are looking for. So that was what was done there. Now move to the next question. It says the 40 centimeter cube of ethanoic acid used in each experiment is measured using a measuring cylinder. Measuring cylinders are available in the following sizes. Okay. So draw a circle around the size of measuring cylinder which should be most suitable to measure 40 centimeter cube. So if you want to measure 40 centimeter cube and you want the most accurate value, you would use the one of 50 centimeter cube because that's the closest to 40. So I'll give you a more accurate value than any others. This is not even close to it because this is far, this is too far, and this is equally far. All right, so that is the answer to that. Most of the gas collected in the measuring cylinder is air rather than carbon dioxide. Explain why air is collected in the measuring cylinder. So air is usually collected in the measuring cylinder so that the gas collected will simply displace it. Okay? And we need that information, we need that so that we can properly measure the volume of gas that has been produced. So why air is collected in the measuring cylinder is so that it is displaced out of the flask. It is displaced out of the flask. Displaced out of the flask by carbon dioxide. Displaced out of the flask by carbon dioxide. That is why air is collected in the. All right. So explain why this does not affect the accuracy of the result. So it doesn't affect the accuracy of the result because the volume of air displaced is the same as the volume of carbon dioxide. So that's what I said, just like I said earlier, we use the volume of the air displaced to determine the volume of carbon dioxide. So it doesn't affect the accuracy of the result because the volume of air displaced is the same as the volume of carbon dioxide. It's the same as the volume of carbon dioxide. So that is why it doesn't affect the accuracy of the results. All right, so that answers that. Okay, now we move forward to the next question. Move forward to the next question. During this experiment, the temperature of the acid decreases slowly. So give a reason why the temperature of the acid decreases and suggest a change to the apparatus used that will minimize the decrease in temperature. So if you look at the setup of this experiment, let's go back to the setup. You see that a conical flask is used here, okay, which is more like a glassware, all right? So it's a glassware, all right? And because of that, there is a decrease in the temperature, all right? So you could simply say that the reason why there's a decrease in temperature is because the flask, which is glass, is not a good insulator. Okay, the glass used, glass is not a good insulator. Or another reason could simply be that it is lost to the surroundings. Okay, the glass is not a good insulator, or it is lost to the surroundings. Okay, that either of them would get you the required score. Okay, and for the fact that the glass is not a good insulator, it means that the flask conducts. So as the flask conducts, it is lost. All right. So what would be the change to the apparatus? So what would be the change to the apparatus is either you insulate the flask, or another idea is to use a water bath, so that you could regulate the temperature, or use a water bath. So either of the two can be adopted. You don't have to write the two of them. Okay, you pick either of them. Either you insulate the flask, or you place the flask in a water bath, because a water bath can help keep the temperature, regulate the temperature the way it should. All right, so that's for that question. So we'll go to question 3. A student tests two substances, solid M and N. Now, test on solid M. Solid M is hydrated chromium-3 nitrate. Okay, hydrated, of course, it means it contains water of crystallization. Now, the student places half of solid M in a boiling tube and heats it strongly. Of course, when you heat it in the boiling tube, the water of crystallization begins to evaporate. Now, the student holds a piece of anhydrous cobalt 2 chloride paper at the mouth of the boiling tube. All right. Now, remember that while eating, what goes up is water, right? Because it's a hydrated solid. And in such case, if water goes out and you take cobalt 2 chloride paper, which happens to be blue, okay, it simply changes because of the presence of water, because this is used to test for water. So observation is changes from blue to pink. Changes from blue to pink. And that should tell you that what is giving off is simply water. And it confirms that because it's a hydrated solid. Now the student inserts a glowing splint into the mouth of the boiling tube. The splint bursts into flames. Now if you've forgotten what, it says identify the gas giving off. Now if you've forgotten the gas that does this, all you need to do is to consult the table of the information given just for the test for gases, because the gas has been given off that can reignite a glowing splint. So you look at it, you see that oxygen is the gas that does that. So you consult the table, and all you need to go is to go back there and fixing the correct answer. All right, so the gas that is likely giving off is oxygen, right? Oxygen. So either you use oxygen or you write O2, either of them get you your mark. But be careful not to write O, as many will always make a mistake, because oxygen is diatomic. All right. Now, the student dissolves the remaining solid M in water to form a solution. Now, remember what the solid M is. It's a chromium nitrate solution. Okay, chromium nitrate solution. Chromium nitrate. All right. Now, the student adds aqueous sodium hydroxide dropwise and then in excess to solution M. So, since it contains chromium nitrate, we have to go back to the table to see what will happen when you add aqueous sodium hydroxide in drops and in excess, and then pick it out from the table. So just go back to the table and see where you add aqueous sodium hydroxide to either nitrate or a chromium. Now, if you look at nitrate, you're adding aqueous sodium hydroxide and you're adding aluminum foil. So this does not rhyme, and you warm carefully. So this does not rhyme with the instruction there. That means we are not testing for nitrate yet. So we'll go and look for chromium. So if you add aqueous sodium hydroxide, of course, this aligns with the test for chromium. So a green precipitate is formed in drops, which is then soluble in excess. So this is what is applicable to the question, and this should be the answer to that. So we go back there and insert the correct answer to that, just by consulting the table. So observations when you add it in drop-wise, what you observe is what? You observe a green precipitate. So what I'll just write here is green precipitate. Green precipitate. Right. And then in excess, just like we have it there, it's what? It is soluble. We say it dissolves. So either of them gets you the full mark for that. Now, the student adds a piece of aluminum foil to the product from B1. The mixture is then warmed. The student tests for any gas produced. What will be the observation? Now, remember that when we consulted the table, we saw an instruction like this, and it was a test for nitrate. Now, let's go and see again. So, we consult the table. We see that it's a test for nitrate. So, we see, yes, add aqueous sodium hydroxide, aluminum foil, and warm carefully. What gas is produced? Ammonia gas is produced. So, what will be the observation if ammonia gas is produced? So, you have to remember the test for ammonia gas. Still consult the table to be sure if you are not sure. Right? So, if you look at the table, how do you test for ammonia gas? Tons, damp, red litmus paper, blue. So, this is the observation that should be inserted into that answer. So, we just go into that question rather. So, we just go back here. You see, the observation is tons, damp, red, litmus, paper, blue. And that's all. So you can see how I'm using the table. And that's the same way you should also learn to use the table to get answers of certain things you are not sure. Even though you are sure, it is still good that you use the table to confirm what you have done. So move to the next set of questions. All right, a lot of tests have been written here. All right, so let's just go straight. Describe how to carry out a flame test. Now, how do you carry out a flame test? First, you need the compound that you want to use, okay, and then you, of course, the flame test is to test for the metal, right? And then you need a non-luminous flame. And then equally, you need something to hold onto the metal you're trying to test for, okay, or whatever ion you're trying to test. All right, so how would you conduct a flame test? So you use a wire, or splint, okay, to get the substance. Use a wire or splint to get the substance into a non-luminous. This has to be mentioned, right? Use a wire or splint to get the substance into a non-luminous flame. And a non-luminous flame is simply a blue flame. All right. So the color of the color produced tells you what kind of substance it is. And of course, you see the flame test table here. All right, for all the metal ions. All right. So the color of the flame will tell you what kind of metal ion we're simply looking at. So that's simply what you need to do. How you could get the 2 marks is that you have to mention that something needs to be used to take the substance into the flame, which is a wire or a splint, and then it has to be a non-luminous flame, which is also known as a blue flame. So the next question says, identify solid N. Now, if you look at solid N, look at what was performed on solid N. When a flame test on solid N, it gave a light green flame. So we'll go and consult which metal ion gives a light green flame. So you see, light green flame is for barium, the barium ion. Okay, so the barium ion. So we'll go back to this point, identify solid M. So you see that solid N simply contains the barium ion. All right. And apart from that, we go back again what other substance is in solid N? So when solid N is dissolved in water, okay, to form a solution, and this solution is divided into 4 portions. All right. Now the second portion of the solution, the first portion, we added dilute sulfuric acid to form a white precipitate, and to the second portion we had nitric acid, dilute nitric acid, and a few drops of aqueous silver nitrate, and a pale yellow precipitate is formed. So from this end, we can simply determine something about the substance N. So we'll simply go back and look at when we add dilute nitric acid and aqueous nitrate, what gives us a pale, which of them gives a pale yellow precipitate? So let's look at the anion that is likely going to give that. All right, so if you look at this, you see that the iodide ion is what falls under that category. Okay, so the yellow precipitate shows that it is the iodide ion. So we see the step here. So we just simply go back there and include I minus, right? Because that's the I minus, right? So these are the ions present in that substance. Okay, so here we have the barium iodide. So this is simply barium iodide. So that's for that question. So go to the last question for this particular paper. Grease away and kitchen clean are 2 solutions used as household cleaners that contain aqueous ammonia. So expect to plan an investigation to find which of the 2 household cleaners contains aqueous ammonia with the highest concentration. So assume that aqueous ammonia is the only alkali in the cleaners. In your plan, include the method you will use, how your results will be used to determine which household cleaner contains aqueous ammonia with the highest concentration. And you are provided with common laboratory apparatus and chemicals. So the first thing you need to do is you're trying to see which of these household cleaners contains the highest concentration of ammonia. So step 1 is, of course, we're going to include the method. Okay, and since we are dealing with aqueous ammonia as an alkali, a weak alkali precisely, of course, what should come to your mind is titration. All right, titration should come to your mind. So you could just write out all the ideas that you need to complete. How many marks does this go for? It goes for 6 marks. So titration is the method that you're going to use. Laboratory apparatus also needs to be mentioned. So of course, apparatus you need. You need the burette, the pipette, okay, the volumetric flask to measure volume, or you could also mention. You also need, of course, you need the indicator. All right, you need every apparatus that fits into titration should be mentioned to also get you some marks. All right, so the first step is, since you are comparing 2 household cleaners, so step 1 is to use equal volumes of the alcohol. So we measure equal volumes. That's the first step. We measure equal volumes. So including your formation, measure equal volumes of the toilet cleaners. Measure equal volumes of the household. Measure equal volumes of the household cleaners into a conical flask. Okay, so you measure equal volume of the household cleaners into a conical. Just going to write this properly. So into a conical flask. So after doing that, okay, so the next step is, after you've measured equal volumes of the household cleaners into the conical flasks, the next step is you have mentioned the flasks that you use to contain it, and of course you measure, and of course you also will need a measuring cylinder or a pipette to do that. Okay, so either you use a conical flask. You use a conical flask to contain what you have measured, and then use a measuring cylinder or a pipette to measure the accurate volumes of each of them. Now, why are we using equal volumes? So that we can properly compare the two household cleaners. Now, after that step, the next step is to add an indicator. So add methyl orange into the solutions. So you add methyl orange into the solutions. Okay, now remember we've indicated the method, and then we've given details of the apparatus that are used in each case. So we add methyl orange into turns from it turns yellow. It turns yellow. Okay, when you add methyl orange into the solutions, it turns yellow. Then add a measured volume of acid, add a measured volume of acid into the solution until the solution turns orange. The solution turns orange. Okay, so when you add the indicator to the alkaline medium, because the household cleaners are alkaline, that contains, you are trying to determine aqueous ammonia there. So it's simply an alkaline medium. It turns yellow. So we're moving from yellow to the neutral, which is the orange color. So when you add the acid into the solution until the solution turns orange, that means you've moved it from the alkaline region or the medium to a neutral medium. All right. Now, when we move to a neutral medium, you need to take note, obtain the volume of the acid, at the start and end of the reading. At the start and end of the experiment, or at the start and end of the titration. Let's say titration. Okay, so the biggest volume there used is the most concentrated ammonia. So the biggest volume has the most concentrated ammonia. Okay, so let's write this properly. So the biggest volume has the most concentrated ammonia. All right, so this is how to get 6 marks for this question. So what have we done? First mark allocated will be the fact that you mentioned that you use equal volumes of the household cleaners. Because for you to be able to compare 2 household cleaners, you have to use the same volume, okay, for you to have a better comparison. And then the second mark goes to you mentioning the right apparatus that you used for your experiment. So in other words, this is like 1 mark, and for the fact that you mentioned the right apparatus, whether the conical flask, the pipette, or the measuring cylinder, gives you another mark. So that's the second mark. Now, the third one is the fact that you mentioned, you are now talking about the method. You added methyl orange into the solution, and you also tell the color of the solution when you added the methyl orange is another 1 mark. All right? Then the next mark is the fact that you added a measured volume of the acid into the solution, okay, until the solution turns neutral, which is orange. Okay, and then, so that's 4 marks. Then you obtain the value at the start and end of the reading, because it's titration. You have to look at the start reading and the final reading. And then the sixth mark is that you indicate that the biggest volume obtained for the from the two experiments, after you have subtracted the start and the finish, the end reading, tells you that that one has the most concentrated ammonia. So this is the end of this particular video. I want you to go through it, watch it over and over again, and share with your friends.
I want to talk about a very important YouTube channel called Ajiro Tech. Trust me, this YouTube channel is a giveaway. It's loaded with IGCSE. Trust me, is a giveaway. This channel is helpful for your group studies, your personal studies, and it has a proven track record of producing excellent results. So do me a favor, click on the subscribe button, okay, and share this YouTube channel with your friend. Trust me, that will be the best gift that you are giving to them. Thank you very much, and I'll see you in my next video. Bye bye.